All right, let's get right into it. In the world of materials science, there's a really common misunderstanding, one that can quietly cost a lot of money, waste time, and even lead to some serious failures. It's all about two words that people often use interchangeably, but they mean totally different things: phase and microstructure. And getting this right isn't just for academics, it's absolutely essential for anyone who designs or works with materials.
So here's the heart of the issue. For a long time, many engineers have treated these terms like they're synonyms. But this isn't just about being picky with words. No, this is a fundamental conceptual error, and it leads to things like flawed analysis, really misleading terminology, and ultimately poor choices when it comes to designing materials.
Okay, so to clear this all up, we've got to start at the most basic level. We're going right back to the fundamental building blocks of a material. So first things first, what exactly is a phase?
The easiest way to think about it is like this. A phase has a very specific chemical recipe, which atoms are in the mix, and a specific atomic blueprint. That's how all those atoms are stacked together. It's the material in its most basic, most uniform state. Kind of like a single, perfectly formed Lego brick.
And this image here, it's the perfect way to picture it. Each one of those little crystalline grains you see is a region where the atoms are arranged in a nearly perfect repeating pattern. That specific arrangement of atoms is the phase. It's really the material's fundamental identity, right down at the atomic level.
Let's make this real with a great example: steel. Now, steel isn't just steel. It's actually made up of different phases, and each one has its own unique crystal structure and its own personality, if you will. You've got the soft, ductile ferrite with its body-centered cubic structure, and then on the other end of the spectrum, you have extremely hard martensite, which has a body-centered tetragonal structure. See, it's the same iron and carbon atoms, but they're arranged in a fundamentally different way, and that difference in arrangement changes everything about its properties.
Okay, so if phases are the fundamental building blocks, what happens when we zoom out a bit? Well, that brings us to the grand design, the overall architecture of the material. And this is where we get into the concept of microstructure.
Microstructure is that next level up. It's not about the building blocks themselves, but all about how they're put together. It describes the whole architecture, the shape of the phases, their size, how they're spread out, and how they all meet at their boundaries. It's the big picture view of the material's internal landscape.
And look at this. This is exactly what I mean. You can see all those individual grains, and each one of those is made of a single phase, like ferrite. But the microstructure, that's the whole picture. The collection of all those grains, their different orientations, and all the boundaries where they meet. It's the city, not just the individual buildings.
Now take a look at these two images. On the left, we've got perlite, with that really distinct, layered, almost fingerprint-like pattern. And on the right, you see martensite, which has a much sharper, needle-like structure. These are two completely different microstructures. They might be built from the same basic iron and carbon atoms, but their arrangement, their architecture, is totally different. And that's what gives the final steel dramatically different properties, things like strength and toughness.
Now this right here, this is where the confusion really kicks in. Look at that perlite again. We call it a microconstituent, which is really just a fancy term for a recognizable feature inside the microstructure. We see it and we give it one name. But if you could zoom in with an incredibly powerful microscope, you'd actually see it's made of two totally separate phases, alternating layers of soft ferrite and hard cementite. So get this, a single feature in the microstructure can itself be a complex mix of multiple phases.
And that brings us to maybe the most important takeaway from this whole explainer, the hierarchy. Understanding this relationship is really the key to finally separating these two concepts for good.
It really is this simple. You can't have a building without bricks, right? But the kind of building you end up with depends entirely on how you arrange those bricks. Phases are the fundamental bricks. The microstructure is the final architectural design. This sequence is the crucial part to remember. It all starts with the fundamental phases. Then, through processes like heat treatment, these can undergo phase transformations. This creates the final microstructure, the specific arrangement of those phases. And it's that microstructure that ultimately determines the material's final properties, like its strength or ductility. You control the phases to design the microstructure to get the properties you want. It's a chain of command.
So, why have we spent all this time hammering on this distinction? Well, because like we said at the very beginning, getting it wrong has real, practical consequences that go way beyond the lab.
When you mix up these terms, you get a whole cascade of problems. You get these vague, confusing terms like second phases that just lump together completely different things. You end up with flawed data from your measurements. You get models that just don't work,
and heat treatment instructions that seem to contradict each other. And at the end of the day, you can't actually predict how a material is going to behave.
And hey, don't just take my word for it. Researchers have been pointing this out directly. Silva and his team, for example, really criticize that catch-all term second phases because it causes engineers to lump together totally different phenomena, like, say, the tiny particles that make steel stronger versus large brittle inclusions that actually make it weak.
Let's take so-called dual-phase steel as a perfect example. The name makes it sound simple, right? Just two phases. But in reality, these advanced steels are way more complex. They can have not just ferrite and martensite, but also bits of retained austenite, bainite, and carbides. That simple label completely hides the complex microstructure underneath. And this isn't just about a name. It means an engineer might miscalculate the steel's true strength or its fatigue life because they're underestimating its complexity. That could lead to over-designed parts or, even worse, unexpected failures down the road.
So there you have it. We've broken it down. Phases are the bricks. Microstructure is the building. This isn't just about terminology. It's a fundamental hierarchy that governs how a material performs. So the question I want to leave you with is this. Now that you're armed with this clarity, how is this going to change the way you think about, talk about, and maybe even design the materials you work with every single day?